Well. Ladies and gentlemen, thank you for joining tonight's stream. I am very excited. Oh, excuse me. What a great way to start, guys. Just greening out immediately as soon as the stream begins. My apologies. It's going to forget to highlight real later. So, this is a tech talk that I've actually kind of done before. This video with Lex Fridman and Sara Segar. It is a really great conversation about exoplanets and a couple of other cool things. So we are just going to dive right in, except, of course, everything in OBS just decided to stop working. So bear with me for a hot second here, guys. Was ist das? Oh, I see. It's picking the wrong source. That's why. Should be doing this. Okay, I think we have gotten through most of the technical difficulties. I should have had all that set up ahead of time. Apologies. So the conversation with Sara Segar and Lex revolves primarily around exoplanets and ends with like all of the feels. And it's a really interesting conversation. We're going to try and meander our way through most of it. So let me get it started. And please, guys, enjoy.
When did you first fall in love with the stars?
I think I've always loved the stars. One of my first memory is of the moon. I remember watching the moon, and I was in the car with my dad, who my parents were divorced, and he was driving me and my siblings to his house for the weekend. And the moon was just following me. Just had no idea why that was.
Yeah. So like looking up at the sky and there's this glowing thing. How do you make sense of the moon at that age?
At age 5, there's just no way you can. I think it's one of the great things about being a kid. It's just that curiosity that all kids have.
You know, I was thinking, because there's these almost out there ideas of that our Earth is flat, floating about on the internet, and it made me think. You know, when did I first realize that the Earth is like this ball that's flying through empty space? I mean, it's terrifying. It's awe-inspiring. I don't know how to make sense of it.
It's hard because we live in our frame of reference here on this planet.
Yeah.
It's nearly impossible. None of us are lucky to go to see the curvature of Earth.
I mean, do you remember when you understood like the physics, like the layout of the solar system? Was it like, did you first have to take physics to really, like high school physics to really take that in?
I think it's hard to say. I had this book when I was a child. It was in French. I grew up in Canada, where French is supposedly taught to all of us English-speaking Canadians. And it was this book in French, but it was about the solar system. And I just loved flipping through it. Yeah. It's hard to say how much, you or I understand when we're kids, but it was really a great book.
What about the stars? When did you first learn about the stars?
I do have this very incredible distinctive memory. And again, it had to do with my dad. He took us camping. Now, my dad was from the UK, and he was the type who you'd find wearing a tie on weekends. So camping was not in his sphere, his comfort zone. Yeah. But we had a babysitter. Every summer we had a babysitter. And one summer we had Tom. He was barely older than we were. He was 14. My brother was 12. I would have been 11 or 10 maybe. And we went camping because Tom said camping's the thing. We should try it. And I just remember I didn't aim to see the stars, but I walked out of my tent in the middle of the night and I looked up and wow, so many stars. The dark night sky and all those stars just like screaming at me.
I will say, like, looking up at the stars as a child was like an incredibly like profound moment and connection to like the universe, and just looking up and wondering what all that was. Like, there was something, like, I know some people believe in magic and mysticism. Like, there was something incredibly magical about these burning little lights that were making their way. And I gotta say, like, even as a kid, like, I remember in my hometown looking up at the sky and always seeing so many stars. And unfortunately, due to like light pollution and other things, you just don't you get to appreciate them as much if you do go camping. So camping is like a real treat. And if you haven't gone and looked at the sky in the last couple of years, highly recommend it, guys. It's very soothing.
I just couldn't believe that. Honestly, like, my first thought was, this is so incredible, mind-blowing. Like, why wouldn't anyone have told me this existed?
Can anyone else see this?
Have you had an experience like that with anything?
Yeah, I've had that. I mean, I don't know if maybe you can tell me if it's the same, I've had that with robots. There's a few robots I've met where I just fell in love with this. Like, is anyone else seeing this? Is anyone else seeing that here in a robot is our ability to engineer some intelligent beings, intelligent beings that we could love, that could love us, that we can interact with in some rich ways that we haven't yet discovered. Like almost like when you get a puppy, hey, you used to have a dog, and there's this immediate bond and love, and on top of that ability to engineer it, it was, I had to just pause and hold myself. I imagine, I don't have kids, I imagine there's a magic to that as well, where it's like a totally new experience. It's like, what?
Well, yeah, the stars, though, unlike kids or the puppy, it's only a good thing.
So you felt, you weren't terrified? Like, to me, when I look at the stars, it's almost paralyzingly scary how little we know about the universe, how alone we are. I mean, somehow it feels alone. I'm not sure if it's just a matter of perspective, but it feels like, wow, there's billions of them out there, and we know nothing about them. And then also immediately to me, somehow mortality comes into it. I mean, how did that make you feel at that time?
I think as a child, without articulating it, I felt that same
That
way.
feeling.
Just like, wow, this is terrifying. What's out there? Like, what is this? What does it mean about us here?
You're a scientist, a world class scientist, planetary scientist, astronomer. Uh, Now, I'm a bit of an idiot who likes to ask silly questions. So some questions are a little bit in the realm of speculation, almost philosophical, because we know so little. And one of the awesome things about your work is you've actually put data and real science behind some of the biggest questions that we're all curious about. But nevertheless, many of the questions might be a little bit speculative. So on that topic, just in your sense, do you think we're alone in the universe, human beings? Do you think there's life out there?
Well, Lex, the funny thing is that as a scientist, I so don't even want to answer that.
You really?
No, I will answer it though.
Yeah.
But I just love to
You're
say,
resistant naturally.
yeah, we know.
So just before we dive into this is like a fun episode to check out. After the other day I was talking about the Fermi paradox and some of the reasons why we might not see intelligent life, specifically like intelligent life that is capable of either leaving signs of like them colonizing or traveling through the universe, or sending us some type of signal, that we could potentially read. That's what like SETI and all these other, guys are set up to try and do.
We naturally resist that because we want numbers and hard facts and not speculation. But I do love that question. It's a great question, and it's one we all wonder about. But I have to give you the scientist answer first,
Yeah, sure.
which is
Respect,
we'll have the
scientist
capability to
answer.
answer that question soon, even starting soon.
How do you define soon?
How do I define soon?
What do you? So much happened in the last 100 years.
Right. And there's a difference, right? If it's 10 years or 20 years or 100 years. Yeah, there's a difference in that. Well, soon could be a decade or 2 decades.
And the
By
answer.
the way, journalists usually don't like that, or the people want like tomorrow, they want the news. But what it's going to take is telescopes, space telescopes, or very sophisticated ground or space telescopes to let us study the atmospheres of other planets far away and to look what's in the atmospheres and to look for water, which is needed.
This is a really important point. Like the instrumentation that we require to make these types of observations like costs money. Like there's a significant investment that needs to be made, in these like different facilities and different technologies that allow us to peer into the universe. And though there are some people who might argue that that seems like a big waste of money and what are we ever going to learn, there have been like numerous scientific breakthroughs that we on Earth have benefited from as a result of looking up at the stars or traveling to space. So it's not to say that it isn't a fruitless pursuit.
Needed for life as we know it, to look for gases that don't belong that we might attribute to life. So we have to do some really nitty-gritty astronomy.
So the promising way to answer this question scientifically is to look for hints of life. That's where like many of your ideas come in, of what kind of hints might we actually see about this life.
Right. That's exactly what we need to do. And I like the word you chose, hint, because it's going to be a hint. It's not going to be a 100% yay, we found it. And then it will take future generations
Okay, just slow down time here.
to do more careful work, to hopefully even find a way to send a probe to these distant exoplanets and to
Jack.
really figure this out for us.
I mean, we'll talk about the details. Those are fun, but like
But back to the speculation,
the
maybe.
zoomed out
Yeah.
big picture.
The zoomed out big
speculation
picture
question.
is yes, I believe absolutely there is life out there somewhere, because the vastness of the universe is incredible. It's so breathtaking. When we look at the night sky, if you can go to that dark sky, you can see, many, many hundred, or even if you have good eyesight and you're somewhere very dark, you could see
Take a look at what
thousands
they're
of
talking
stars.
about here.
But in our galaxy, we have hundreds of billions of stars,
There's one.
and our universe has hundreds of billions of galaxies. So think about all those stars out there.
There's our galaxy.
And even if planets are rare, even if life is rare, just because the number of stars is so huge, things have to come together somewhere, someplace in our universe.
Yeah, it's so amazing to think that somebody might be looking up on another planet in a distant galaxy.
See, that I will say is almost for sure. There is definitely many life forms that are looking up at the same stars and to a certain extent looking at each other. It's just a question of how long ago it was or how much time needs to pass before alien civilizations might receive the light that's reflected off of our planet.
Oh,
I have
we're
to
in a distant
interrupt your
solar
reverie and get back to, in our lifetime at least, the short term.
Yeah.
We only have the nearest stars to look at. It's true that there are so many stars, so many hosts for planets that might have life. But in the practical question of will we find it, it has to be a star quite close to Earth, like a few light years, tens of light years, maybe hundreds of
Quite
light
bright.
years.
It's
And by the way, yeah, you've introduced me to a tool of eyes on exoplanets, I think, that NASA has put together.
Eyes on
JPL.
exoplanets. It's a
Eyes on
great
exoplanets.
software. You can
It's
download
so cool. But anyway, can you give a sense of like who our neighbors are? Like you said, hundreds of light years. Like how many stars are close by? Like what's our neighborhood like? We're talking about 5, 10 stars that we might actually have a chance to zoom in on.
I'm talking about maybe a dozen or 2 dozen stars
And that's
with planets that look suitable for us to follow up in detail.
for life.
Right.
Okay.
But one thing that's really exciting in this field is that the very nearest star to Earth, called Proxima Centauri,
Oh, let's go here.
it's
This
part
is
of the
cool.
Alpha Centauri star system,
Cool name, by the way.
Yeah,
I mean,
Proxima.
Whoever names them.
nearby.
Oh, okay.
Nearby,
But it sounds cooler.
But
than
Proxima Centauri appears to have a planet around it. That's about an Earth mass planet in the so-called habitable zone, or the Goldilocks zone of the host star. So think about how incredible that is. Like out of all the stars out there, even the very nearest star has planets and has a planet of huge interest to us.
I think this is
Yeah.
Proxima
Okay. So
B
can we
over
talk
here.
about that planet? What
Proxima C
what
is
what does
the
it mean to
Proxima.
be maybe possibly habitable? What is how does size come into play? How does what we know about gases and what kind of things are necessary for life? What are the factors that make you think that it's habitable? And by the way, I mean, maybe one way to talk about that is people know about the Drake equation, which is a very high level, almost framework
Wow,
to
that's
think about
beautiful.
what is the probability that, correct me if I'm wrong, that there's life out there, and intelligent life, I think. I don't know. But then you have an equation named after you now, which I think nicely focuses in on the more achievable and interesting part of that question, which is on
shit.
whether there's habitable planets out
Oh,
there,
this one,
or
yeah.
how many, I guess,
Right, yeah.
habitable planets are.
So the funny thing was one time I met Frank Drake, and I asked if
wow,
he
this is
minded if
wild.
I took his equation and kind of revamped it for this new field of exoplanet astronomy.
This is
He was totally cool with
crazy.
it. He's-
This is a
He got
game
total approval.
changer.
Well, maybe. Okay,
Oh
so
my
sorry.
I'm not
I-
sure if he'd actually read the stuff about my equation, but he was cool with it. He was
He
cool.
was cool with it.
Oh my
Uh,
god.
Okay, so I just said like 15 different things, but maybe can you tell from your perspective what is the Drake equation?
Okay. So Ocelot, just This is like the cool. Like my mind is actually blown right now by this star map, and just like this is something I've actually been looking on stream to illustrate, like the insane scale. And I know people are like, "Yeah, we get it, it's big," but this is truly like, if this is the now again, I think what was that? That was Proxima, which is what they're talking about. So this is one of the nearest, planets that essentially exists within the habitable zone, right? And if we zoom out here, you can see we start to leave that solar system, and now we're starting to see some of the stars that would be around us. So we would be somewhere within this small little group. This would be our, galactic local group. This is the Milky Way galaxy. I wonder, can you actually I don't think I can shift the perspective, and that's okay. There's your Milky Way, and as we zoom out, you can see the Milky Way and its subsequent systems as well that are around it. Now we're getting to the level of this is like just straight up the universe as we know it, and all the objects mapped around. So the scale of it is just wild. This is such a cool view. Thank you for unlocking that wonderful thing. That was great.
And what is, the Segar equation?
Sure. Well, the Drake equation, as you said, it's a framework.
Give me 1 second.
It's a description of the number of civilizations out there, of intelligent beings that are able to communicate with us by radio waves. So if you think of the movie Contact, you've seen Contact, right? We're hoping to we're listening in, actually. It's an active field of research, listening to other stars at radio wavelengths, hoping that some intelligent civilizations are sending us a message. And the Drake equation came at the start of that whole field to put the factors down on paper to sort of illustrate what is involved to kind of estimating. And there's no real estimate or prediction of how many civilizations are out there, but it's a way to frame the question and show you each term that's involved. So I took the Drake equation and I called it a revised Drake equation, and I recast it for the search for planets by more traditional astronomy means. We're looking at stars, looking for planets, looking for rocky planets, looking for planets that are the right temperature for life, looking for planets that might have life that outputs gases that we might detect in the future. It's the same spirit of the Drake equation. It's not going to give us any magic numbers.
Oh, interesting. Okay.
It's not going to say, hey, here's exactly what's out there. It's meant to kind of guide of where we're going.
Although the Drake equation the initial equation proposed actual numbers for those variables, right?
Oh, yes, the equation proposed numbers, and you can still plug your own numbers in. And there's this really cute website that lets you, for both the Drake and my revised equation, plug in some numbers and see what you get. So, yeah.
So what are the variables, but maybe also what are the critical variables?
So in my equation, I set out to what are the numbers.
So just to recap, they're talking about the Drake equation, which is a very rough way of estimating the potential of life that could be in the universe. And it essentially is like, if there's this many galaxies, you can assume there's this many stars, you can assume there's this many planets. The Sara Segar version of it obviously elaborates a little bit more on the complexity or the levels of dimension in order to measure that. So
of inhabited planets that show signs of life by way of gases in the atmosphere that can be attributed to life. I could just walk through the terms. That's probably simpler.
That's probably
the first thing I say is, what are the number of stars available? And it's not that those trillions and trillions of stars everywhere. It's what are available to a specific search. And so, for example, the MIT-led NASA mission TESS is surveying the sky, looking for all kinds of planets, but it also has stars. It has about 30,000 red dwarf stars. So we just take a number of stars that a given survey can access. So that's what the number of stars is. Then I wanted to know what kind of stars are quiet. I called it fraction of those stars that is quiet. In the case of TESS, the way it's looking for planets is planets that transit the star. They go in front of the star as seen from the telescope. But it turns out that some stars are very active, they're variable, and they brighten and dim with time, and that interferes with our observation.
I apologize to interrupt. So it's a transiting planet. So you're really looking for a black blob, essentially, that blocks the light,
We're looking for a black blob that blocks the light. Mhm.
and then trying to say something about
That's
the
a nice
size
way
of
to
the
put it.
planet from the frequency of that black blob's appearance and the size of that black blob, that kind of thing.
Yeah, but let's just say that out of all the stars there are accessible to whatever telescope, some of them are just bad. For whatever reason, you're not going to be able to find planets around them. So I need to know the fraction of those that are good. So again, we have the number of stars, the fraction of them that we can actually find planets around.
And by the way, is our sun one such? Is our sun quiet?
Our sun is quiet.
Okay, good.
So
to
I have
know.
actually two terms. One describes how quiet they are, and one is if we can find a planet around that star. These transiting planets, for example, not all planets transit, because the planet would have to be orbiting that star in this kind of plane, as viewed from you. But if a star is, for example, orbiting in the plane of the sky, it will never transit. It will never go in front of the star.
Right.
So in that case, we have to have a fraction that
See if we can
takes
find
into
a planet
account
just randomly
of
picking a
that
star
kind of
here.
geometric factor.
And hopefully, I mean, you can assume that it's uniformly distributed. Hopefully.
Yes, we can assume, and there's evidence that it's uniformly distributed, yes. So then so all of these factors so far, number of stars accessible to whatever telescope you're thinking about, how many stars are quiet, fraction of stars that are quiet, fraction that are observable, in this case for the geometric factor. Those are all things we can measure. And there's one more term in the Segar equation we can measure. I call it fraction of planets in the habitable zone. Because believe it or not, we have a handle on that for a certain set of stars. We know from the Kepler Space Telescope that operated for a number of years, we have estimates for how many planets are in the so-called habitable zone of the host star.
So yeah, the habitable zone essentially is a Goldilocks zone, or a distance from a star, and it would be different from each star because all stars are the specific shape, a certain density. They may be made of different gases that perform different radiations. So different planets need to be a different distance away for it to be in the habitable or Goldilocks zone. But there are a lot of assumptions being made in that, in the sense that, you got to remember, for a long time, human beings, we thought that, life cannot exist in certain types of conditions. And one of the interesting things that we found about studying the bottom of the ocean and deep, aquatic life, when we see these coral that have, volcanic gases that are superheated to hundreds of degrees, just bubbling up from the magma that's under the crust, they actually find life forms, small little bacteria and visible life that live off of the gases and the things from these super hot structures. So we would assume that there's a certain temperature range for life to actually be able to exist. But our assumptions could also be way off. So a lot of this stuff is it's fun, intellectual play, but I think it's very difficult for us as humans to conceptualize what the different forms of life could be and how they could manifest themselves.
Star for a certain type of star. So all those we have measurable. And then, like the Drake equation itself, there are some terms we can not measure. And those ones, I call them FL, fraction of all those planets that have life on them.
There you go.
Because we don't know what that is. And FS, I called for spectroscopy, the fraction that we can use our telescope and instrument tools to look for light. Actually, FS was the planets that have life that actually gives off a gas, a useful gas that might accumulate in the atmosphere, so we could eventually observe it.
How do the FL and FS interplay? So these are separate terms?
Separate terms.
And so
for example, you could imagine life like us humans. We breathe out carbon dioxide. But our planet Earth, we already have a lot of carbon dioxide on it. Well, we have hundreds of parts per million, but it has a really strong signal. So us humans breathing out carbon dioxide, it's not helpful for any intelligent beings that are looking back at Earth, because there's already enough carbon dioxide. We're not adding to it. So if there is life on a planet, and it's outputting a boring gas that's not helpful for us to uniquely identify as being made by life versus just being there anyway, then it's not helpful. So I separated those two terms out. Soon, I think we'll have evidence that planets that can support life, at least, are common.
So, okay, this is such an awesome topic. I have a million questions. What? Okay, I know it's a little bit of speculation, but what's your sense about that? I think FS, which is like that life would produce interesting gases that would be able to detect. Like, is there one? Is there scientific evidence, and second, is there some intuition around life producing gases, detectable hints in terms of chemistry?
So interestingly enough, that entire question relates to, I'm going to say, almost my life's work,
Yeah,
like the work I'm doing now and the work I'm doing for the next 20 years. And I
yeah.
wish I could give you a concrete number, like 1%. Like on the worst days, it's 1%, let's say, in my mind. On the best days, it's like 80%. And I could actually go into a lot of detail here, but I'll just give you the simplest things. So, first of all, we make an assumption that, like us and our life here on Earth, life uses chemistry. So, we use chemistry because we eat food, we breathe air, and we have metabolism that to break down food to get energy, to store energy, and then ultimately to use it. And all life here has some kind of byproduct in doing all that, some kind of waste product that goes into the atmosphere. So I like to think that life everywhere uses chemistry. Some people have imagined, like, let's imagine like a windmill, like mechanical energy, just getting energy and using it without storing it. And if there was life like that, it might not need to output a gas. So we make this basic assumption of chemistry. That's the first thing. The second, more complicated thing that I and my team work on is what happens to the gas once it is produced by.
Oh, sorry, I did not mean to pause there, but this is a very interesting question, right? Because when you look at the way, like, if you were an alien civilization, right, and you looked at the way humans breathe in oxygen and expel CO2, and then you were to look at plants, and you're like, okay, plants like breathe in CO2 and expel oxygen. What gas would you look for in the atmosphere, right? You're going to be looking for an oxygen-rich atmosphere. You might not be detecting the carbon. So what are you actually detecting? Are you saying, oh, there's going to be like some kind of photosynthesizing plant life that, based off of our understanding of chemistry, is converting energy from one form to another through blah, 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 blah. Anyway, it's interesting suppositions to make for sure.
By life, it goes into the atmosphere. And a lot of gas is just destroyed immediately, actually, by ultraviolet radiation or by oxygen. Oxygen is incredibly destructive to a lot of gases. So
this is actually a good point too. Yeah, like oxygen is toxic. Like at a certain amount of O2 in the air, it actually becomes lethal to you. The majority of our atmosphere, I believe, is comprised of nitrogen. There's a little bit of CO2 in it, but not too much. Yeah, fun fact.
Gas can be produced by life, but it could be just completely destroyed by its environment.
I guess we should pause on that. That you mentioned your life's work. I mean, this is just a beautiful idea. That it's kind of paralyzing when you look out there and you wonder, is there life out there? It's the first paralyzing. Actually, before I encountered your work, I feel like an idiot. But it feels like there's no tool to answer that question. And then what you kind of provided is this cool idea that it might be possible to answer that by looking at the gases. I mean, that's a really interesting, that's a beautiful idea. And yeah, so we could just pause on
Let's pause on that.
that's as a powerful tool, I think, that to build the intuition around, because I was totally clueless about it, and that was it's kind of exciting. I mean, I'm sure there's a folks probably early on in your life who were very skeptical about this notion. Well, maybe I'm not sure, but generally you would want to be skeptical. It's like, well,
I will say Lex is a little bit off base here. Scientists for many years have been able to detect, right, the type of atmospheres based off of analyzing what they call spectroscopy. So what they can do is they can analyze the light, and based off of the type or the way I think I lost my mic there for a sec. Based off the type of light that we see in telescopes, we can use, analyzing the spectrum to determine what gases are in that atmosphere. And the way that we can verify these assumptions are by applying the same techniques to planets that are near us, like Neptune, like Uranus, like Jupiter, Saturn. Like we know what those gases are, excuse me, and we can use the same technology to essentially, figure out like, okay, these are the composition of these planets. So you take those concepts and you extrapolate them out to these far off objects, and that's how we're able to deduce within a certain amount of reason or a certain amount of certainty that's what's out there. It's a really, really cool technology. But I will say, Lex is impressed. Oh, this is super cool. This has been around for some time. We've been doing it for a while. We're going to skip ahead to the exoplanets conversation because this part's fun.
Okay, but how do you detect that type of gases that are on a planet from a distance?
And that's going back to that. That's what people were skeptical about. When I first started working on exoplanets a long time ago, people didn't believe we would ever study an exoplanet atmosphere of any kind. And now dozens of them are studied. There's a whole field of people, hundreds of people working on exoplanet atmospheres, actually.
Wow. So
And
first,
so,
there was a
yes.
point where people didn't even know there was exoplanets, right? When was the first exoplanet detected?
The first exoplanet around a sun-like star, anyway, was detected in the mid-1990s.
There you go.
That was a big deal. Kind of vaguely remember that.
Well, at the time, it was a big deal, but it was also incredibly controversial because in planets, we only had one example of a planetary system, our own solar system. And in our solar system, Jupiter, our big, massive planet, is really far from our star. And this first exoplanet around a sun-like star was incredibly close to its star. So close that people just couldn't believe it was a planet, actually.
Interesting.
So maybe zoom out. What the heck is an exoplanet?
An exoplanet is our name, is the name that we call a planet orbiting a star other than our sun.
Right. Extrasolar, I guess, is
You
another.
can call it extrasolar.
Okay.
Exoplanet is simpler. But I think it's worth
I like how she checks in
pausing
there.
to remember that each one of those stars out there in our night sky is a sun.
Right.
And our sun has planets, Mercury, Venus, Earth, Mars, etc. And so for a long time, people have wondered, do those other stars or other suns have planets? And they do. And it appears that nearly every star has a planet we call exoplanet. And there are thousands of known exoplanets already.
So there's already, there's so many things about space that it's hard to put into one's brain because it starts filling it with awe. So yeah, if you visualize the fact that the stars that we see in the sky aren't just stars, they're suns, and they very likely, as you're saying, would have planets around them.
To touch on this concept really quick, like it makes sense. Like if we can see that our solar system has sort of evolved a certain way in terms of, a sun has gravity, attracts objects, a bunch of shit kind of smashes together, and over time settles into this beautiful ornamental dance of planets just kind of stepping around each other. It is almost a process of evolution, like similar how life has evolved in the universe, evolved on the Earth. The universe has sort of evolved almost its own cellular biology, if you will, in the sense that like planets form in a particular fashion, and we can see that consistently as we continue to like look out into the stars.
There's all these planets roaming about in this like dimly lit darkness with potentially life. I mean, it's just mind blowing. But maybe can you give a brief like history of discovering all the exoplanets? So there's no exoplanets in the 90s. And then there's a lot of exoplanets now. So how did that come about?
So many planets. How did it come about? Well,
Maybe another way to ask is, what is the methodology that was used to discover them?
I can say that. But I'd like to just say something else first, so in exoplanets, the line between what is considered completely crazy and what is considered mainstream research, legit, it's constantly shifting.
This is awesome, yeah.
So before, when I started on exoplanets, it was still sketchy. Like it wasn't considered a career or a thing.
That's a really interesting like precipice to be on in science, not to be someone who's necessarily like studying like a very well established field or building on like a really well verified body of work. You have like really cool scientists like Sarah who are just like charting into stuff that some people might consider like kooky, maybe similar to like Einstein thought black holes that couldn't exist, but then people are like, I'm sorry, dude. Speaking of black holes, as we dive out of one here,
A place where you should be investing.
Yeah.
And right now, today, it's so many people are working in this field. A good, I don't know, at least 1,000, probably more. I don't know if that sounds like a lot to you, but it's a lot.
No,
But-
so it's a legitimate field of inquiry.
Yeah, legitimate field of inquiry. And what's helped us is everything that's helped everyone else. It's software, it's computers, it's hardware. It's like our phones. You have a fantastic detector in there. Like they didn't always have that. I don't know if you remember the so-called olden days. We didn't have digital cameras. We had film. You take a film camera, you send the film away, and eventually it comes back, and then you see your pictures, and they could all be horrible. Yeah.
So yeah, digital. It just changed everything. Data changed everything.
Yeah. And so one thing that really helped exoplanets were detectors that were very sensitive, because when we're looking for the transiting planets.
So a couple things to touch on there really quickly. Number one is yes, like the technology that we use to build these type of detectors and look into the universe and see these kinds of things directly benefit us on Earth. Like it gives us the ability to have more powerful devices in our pockets, more computation at our fingertips. And the other interesting thing to think about as well is that, we as a human civilization, our sun will explode someday. The sun is going to blow up. It might be in billions of years, but it is going to happen. And if humanity wants to survive, we will have to figure out a way to leave our solar system. We will have to find a way to spread out amongst the stars. So it's fair to reason that it's not a bad idea to start looking for places that we could go, or at least understanding like the landscape in which we will be embarking on a true, if you're excited about Star Trek at all, talk about a new frontier, right?
What we're doing is we're monitoring a star's brightness as a function of time. It's like taking a picture of the stars every few seconds or minutes. And we're measuring the brightness of a star, like every frame. And we're looking for a drop in brightness that's characteristic of a planet going in front of the star and then finishing its so-called transit. And to make that measurement,
Go back to
we have to have
Proxima.
precise detectors.
And the detectors that are making the measurement, can you do it from Earth? Is it are they floating about in space? Like what
Both,
kind
actually.
of telescope?
Both. So on the ground, people are using telescopes, small telescopes that are almost just like a glorified telephoto lens. And they're looking at big swaths of the sky. And from the ground, people can find giant planets like the size of Jupiter. So it's about 10 to 12 times the size of Earth. We can find big planets because we can reach about 1% precision. So I'm not sure how technical you want to get, but
Well, yeah. Well, how many pixels are we talking about? Like what? You mentioned phones. There's a bunch of megapixels, I think.
so for exoplanets, you want to think about it as like a pixel or less than a pixel. We're not getting any information. But to be more technical, our telescope, spreads the light out over many pixels, but we're not getting information. We're not tiling the planet with pixels. It's just like a point of light, or in most cases, we don't even see the planet itself, just the planet's effect on the star. But another thing that really helped was computers, because transiting planets are actually quite rare. I mean, they don't all go in front of their star.
Right.
And so to find transiting planets, we look at a big part of the sky at once, or we look at tens of thousands
by
or hundreds of
transiting
thousands,
planet,
or even in some
I
cases,
guess.
millions of stars at one time. And so, you're not going to do this by hand, going through a million stars, counting up the brightness. we have computer software and computer code that does the job for us and looks for counts the brightness and looks for a signal that could be due to a transiting planet. And, I just finished a job called Deputy Science Director for the MIT-led NASA mission TESS. And it was my purview to make sure that we got the planet candidates, the transiting light curves, out to the community so people could follow them up and figure out if they're actual planets or
hard to
false
navigate
positives.
Also publish the data so that people could just
Yeah, publish the data.
all the data scientists out there could crunch and see if they can discover
Exactly.
something.
They can discover something. And in fact, the NASA policy for this mission is that all the data becomes public as soon as possible. So anyone could act. It's not as easy as it sounds, though, to download the data and look for planets.
It's easy to lose
But
you
there is a
if you
group called
expose it instead of
planethunters.org, and they take the data and they actually crowdsource it out to people to look for planets. Yeah, and they often find signals that our computers and our team missed.
That's pretty cool.
So we mentioned exoplanets. What about Earth-like, or I don't know what the right distinction is. If is it habitable or is it Earth-like planets? But what are those different categories, and how can we tell the difference and detect each?
The other video that we did with Catherine DeClure, I think is how you pronounce her name, she loved talking about moons. And I never understood how like cool moons were until she got into a very passionate conversation about them. And I think, she kind of doesn't really like to discern between moons and planets, and she thinks all the objects in the universe are fascinating, which is a vibe that I'm super into. But let's check out Io, because it's a real favorite of mine to explore while talking about exoplanets. It's definitely not Earth-like.
Right. So we're not at Earth-like planets yet. All the planets we're finding are so different from what we have in our solar system. They're just easier planets to find. But like,
In which way?
for example, there could be a Jupiter-sized planet where an Earth should be. We find planets that are the same size as Earth, but are orbiting way closer to their star than Mercury is to our sun. And
So
they're so close that, because close to a star means they also orbit faster. And some of these hot super Earths, we call them, their time to go around their star is less than a day. And they're heated so much by their star. They're heated so much by the star, we think the surface is hot enough to melt rock. So instead of running out by the bay or the river, you'll have like liquid lava. There'll be liquid lava lakes on these planets, we think.
And life can't survive.
Way too hot. The molecules for life would just be molecules needed for life just wouldn't be able to survive those temperatures. We have some other planets. One of the most mysterious things out there,
This is so cool.
factoid, if you will, is that the most common type of planet we know about so far is a planet that's in between Earth and Neptune size. It's 2 to 3 times the size of Earth. And we have no solar system counterpart of that planet. That is like going outside to the forest and finding some kind of creature or animal that just no one has ever seen before, and then discovering that is the most common thing out there.
Interesting.
And so
That's
we're
a
not
very
even sure what they are. We have a
fascinating
lot of thoughts as to the different types of planet it could be, but people don't really know.
I mean, what are your thoughts about what it could be?
Well, one thought, and this is more when we want to be rather than might be, is that these so-called mini Neptunes, we call them, that they are water worlds, that they could be scaled up versions of Jupiter's icy moons, such that they are planets that are made of more than half of water by mass.
So, yeah, and what's the connection between water and life and the possibility of seeing that from a gas perspective?
Okay, so all life on Earth needs liquid water. And so there's been this idea in astronomy or astrobiology for a long time called follow the water, find water. That will give you a chance of finding life. But we could still zoom out, and the community consensus is that we need some kind of liquid for life to originate and to survive, because molecules have to react. If you don't have a way that molecules can interact with each other, you can't really make anything. And so when we think of all the liquids out there, water is the most abundant liquid in terms of planetary materials. There really aren't that many liquids. Like I mentioned, liquid rock, way too hot for life. We have some really cold liquids, like almost gasoline, like ethane and methane lakes that have been found on one of Saturn's moons, Titan. That's so cold, though. And for exoplanets, we can't study really cold planets because they're just simply too dark and too cold.
Interesting. That's an interesting way of putting it. Let's take a quick peek at Titan, because Titan is a very fascinating moon as well. And again, like she's obviously an expert in this space. And the conventional wisdom is, yes, these planets are maybe too cold to support life, but we don't really know. Like there could be fascinating forms of organic life that are just difficult for us to even conceive of, because the conditions in order for them to form would be vastly different. All of that being said, it probably makes a lot of sense for us to look for life as we know it, particularly if we want to try and communicate with it, interface with it, and understand it.
So we usually are just left with looking for planets with liquid water.
What a
And
beautiful little object.
to your
eh?
point,
Look how
it's,
beautiful that is.
you remember we talked about how planets are less than a pixel in that way to say. So we can't see oceans on a planet. We're not going to see continents and oceans, not yet anyway. But we can see gases in the atmosphere. And if it's a small rocky planet, and this is going into some more detail, if we see a small rocky planet with water vapor in the atmosphere, we're pretty sure that means there has to be a liquid water reservoir, because it's not intuitive in any way, but water is broken up by ultraviolet radiation from the star or from the sun. And on most planets, when water is broken up into H and O, the hydrogen, will escape to space. Because just like when you think of a child letting go of a helium-filled balloon, it floats upwards. And hydrogen's a light gas and will leave from the planet. So ultimately, if you have water, unless there's an ocean, like a way to keep replenishing water vapor in the atmosphere, that water vapor should be destroyed by ultraviolet radiation.
Got it. So there's a need for a liquid. I mean, I guess is water. Well, is water essential, or is it other liquids? I mean, the chemistry here is probably super complicated.
Well, there's not an infinite number of liquids.
Right.
There's maybe like 5 liquids that can exist inside or on the surface of a planet. And water is the one that exists for the largest range of temperatures and pressures. Okay. And it's also the easiest type of planet for us to find and study is one with water vapor, rather than a cold planet that has ethane and methane lakes.
What's your personal, in terms of solar systems and planets, that you're most hopeful about in terms of our closest neighbors, that you kind of have a sense that there might be somebody living over there, whether it's bacteria or somebody that looks like us?
I'm hopeful that every star nearby has a planet.
Has some life.
Because it almost has to, for us to make progress. We have to have that dream condition.
So the dream...
That's an interesting point as well. Like, in order for us to potentially, like, detect or contact or find, other places to live, it stands to reason that we would need exoplanets to essentially exist around every single star, for there to be, like, enough of them, close enough, etc., etc.
Dream condition is like life is just super abundant out there.
Yeah, the dream condition is that life is super abundant, and it's based on the thought that if there is a planet with water and continents, that it also has the ingredients for life, and that the kind of base kernel thought is that if the ingredients for life is there, life will form. That's what we're holding on to.
With a relatively high probability.
Yes, that's it.
Okay, let's go into land of speculation. What about intelligent life? Us humans consider ourselves intelligent, surprisingly, or unsurprisingly. Do you think about, from your perspective of looking at planets from a gas composition perspective, and in general of how we might see intelligent life, and your intuition about whether that life is even out there?
I think the life is out there somewhere. The huge numbers of stars and planets. I like to think that life had a chance to evolve to be intelligent. I'm not convinced the life is anywhere near here, only because if it's hard for intelligent life to evolve, then it will be far away by definition.
Well, the sad thing is, maybe from the artificial intelligence perspective, is it makes me sad there might be intelligent life out there that we're just not... Like, the pathways of evolution can go in all these different directions where we might not be able to communicate with it, or even know that it, or even detect its intelligence, or even comprehend its intelligence. Yeah, I'm convinced cats are more intelligent than humans.
Well, what's funny is, like, and I don't want to say this is a failure of imagination on Lex's standpoint, but for someone who, like, studies, like, computers and distributed computing, like, it does stand to reason that there could be interesting physical structures that exist on other planets that we necessarily couldn't conceive of that could have, like, life. So you could think of, for example, like, energy that could be stored in crystals, or gaseous, these, like, vapor beings that exist between different salinities of different gases, and through some chemical process are able to have, life and consciousness and all these other fun things. So there's all kinds of interesting ways of life perhaps even have a distributed nature to its consciousness. So again, there's a lot to imagine there. So I'm not accusing Lex of not having an imagination in this space, for sure.
That we're just not able to comprehend the measures, the proper measures of their intelligence?
My dog is so funny. He's a golden doodle. His name's Leo. We joke that he's either a really dumb dog. And sorry, he's not here to defend himself, but he's either really dumb or he's a super genius just pretending to be dumb.
Yeah, I mean, it's
Because
possible he's a some multidimensional projection of alien life here monitoring one of the one of the top scientists in the world trying to find aliens just to make sure just to make sure that humans don't get out of hand.
that's funny. Oh, I'm definitely going to go in and ask him about that. Ask him about that when I get
She's
home.
on to something. Yeah. What might we look for in terms of signs of intelligent life from your toolkit? Do you think there are things?
So this is something that like we touched on in the Fermi paradox video, right? Is how what would be the signs of life? So she previously touched on, we might see certain gases in certain atmospheres. We might see certain changes in the brightness of certain objects. But, we would hope to see at some point that there's some kind of like evidence of, colonization across the universe, that we'd be able to capture, whether it's like, a spaceship or signs of spaceships flying through the universe, or whether we'd be able to capture, distant structures, let's say, out in the galaxy. And thus far, we have been unable to find anything like that. So it's interesting to hear what they have to think or have to say here.
That we might be able to use, or maybe in the next couple of decades discover, that would be different than life that's like bacteria, that's primitive life.
I still love SETI, Search for Extraterrestrial Intelligence. I like to hope that if there is a civilization out there, they're trying to send us a message. I think, think about it. I don't know. What are your thoughts? Like, if you think about our Earth, there's no structure we've built that intelligent civilizations could see from far away. There's literally nothing, not even the Great Wall of China. And so to think, why would this other civilization build a giant structure that we could see?
Yeah, so with SETI, the idea is that we're both trying to hear signals and send signals, right? Or
Well, we haven't sent one. They call that METI, messaging. And there's a big kind of fear over METI because do you want to tell them you're here? It's kind of this let's wait till they call us.
Yeah.
So
it's
we
like
should
the
be
dating game. You have to how many days do I wait before I call, kind of thing. Okay.
Yes, it is. And so, but the funny thing is, if no one's sending us a message, if everybody's only listening, how do you make progress?
That's right. And but there's the Voyager spacecraft. So we have these little pixels of robots flying out all over the place. Some of them, like the Voyager, reach out really far.
Check.
And they have some stuff on them. Okay.
Here we go.
We do. We have the Voyager, but they're not really going anywhere in particular, and they're moving very, very slowly on a cosmic scale.
We touched, I think, on Voyager in the Fermi paradox video. Like, Voyager's actually picked up some interesting signals, but it has essentially left our solar system. But to your point, it's traveling incredibly slow. Its batteries are running out. The camera doesn't work anymore, and we don't know how long we'll be able to actually sustain contact with it.
And me saying they're far is kind of silly.
Yeah, it's all relative in astronomy. It's all relative, yeah.
Yeah, so if we look at Earth from an alien perspective, from visually and from gas composition, I wonder if it's possible to determine the degree of maybe productive energy use. I wonder if it's possible to tell how busy these Earthlings are.
Well, let's zoom out again and think about oxygen. So when cyanobacteria arose billions of years ago and figured out how to harness the energy of the sun for photosynthesis, they re-engineered the entire atmosphere. 20% of the atmosphere has oxygen now. That is a huge scale. They almost poisoned everything else.
To try and put that in perspective, that is bacteria on Earth re-engineering, right, the atmosphere to the point in which we're probably terrified of the changes that we're making, right, as a civilization, with global warming and just all of the other catastrophic effects of the way that we change the environment. It isn't the first time that this has happened, and we aren't the only life forms that are culprits in this bad game.
Making this what was apparently very poisonous to everything that was alive. But imagine, so are we doing anything at that scale? Like, are we changing anything at like 20% of the Earth with a giant structure, or 20% of this, or 20% of that? Like, we aren't actually.
Yeah, that's humbling to think that we're not actually having that much of an impact.
I know, but we are, because in a way we're destroying our entire planet. But it's humbling to think that from far away, people probably can't even tell.
But from the perspective of the planet, when we say we're destroying, global warming, all that kind of stuff,
There we go.
what we really mean is we're destroying it for a bunch of different species, including humans. But I think the Earth will be okay.
Yeah, we're making it uninhabitable for a large swath of species that have evolved based off of the things like atmospheric conditions and the acidity of the water, and et cetera, et cetera. Life will always find a way. There's no doubt about that. Unfortunately, it's like George Carlin always used to say, the planet will be fine. The people are fucked.
The Earth will remain. Whatever happens to us, the Earth will still be here.
And it'll still be difficult to detect any difference. It's sad to think that if humans destroy ourselves, except potentially with nuclear war, it would be hard to tell that anything even happened.
Yeah, it will be hard to tell from far away that anything happened.
What are your thoughts? Now this is really getting into speculation land. You've mentioned exoplanets were in the realm of, there's this beautiful edge between science and science fiction that some of us, a rare few, are brave enough to walk. I think in academia you were brave enough to do that. I think in some sense artificial intelligence sometimes walks that line a little bit. There is so much excitement about extraterrestrial life and aliens in this world. I mean, I don't know how to comprehend that excitement, but to me it's great to see people curious, because to me extraterrestrial life and aliens is at the core a scientific question, and it's almost looks like people are excited about science. They're excited by discovery,
Right?
and then the possibility that there's alien life that visited Earth or is here on Earth now is excitement about discovery in your lifetime, essentially. I mean, what do you make of that? There's recent events where DARPA or DoD released footage of these unmanned aerial phenomena, they're calling them now, UAP. They got everybody